So today we are going to see Dirichlet condition. The Dirichlet condition is a necessary condition for a function f of x to be applicable for Fourier series. A function f of x is equal to a naught by 2 plus summation n equal to 1 to infinity a n cos n x plus b n sin n x, where a naught, a n, b n are constants, provided if it is periodic, single valued and finite. The second condition is it has a finite number of finite discontinuities in any one period and has no infinite discontinuity. And the third condition is f of x has at the most a finite number of maxima and minima. Now let us consider the problem. Determine the Fourier series for the function f of x equal to x square of period 2 pi in the interval 0 less than x less than 2 pi. So in the interval 0 to 2 pi, the formula for finding Fourier series is f of x is equal to a naught by 2 plus summation n equal to 1 to infinity a n cos n x plus b n sin n x, where a naught equal to 1 by pi integral 0 to 2 pi f of x dx. Suppose the interval is given by 0 to 2l. This a naught formula can be written as 1 by l integral 0 to 2l f of x dx. And that way we can write. Okay. Now integral 0 to 2 pi f of x dx, that is integral 0 to 2 pi x square dx. Here we can apply the formula, very basic integration formula. Integral x power n dx is equal to x power n plus 1 by n plus 1. Using the very basic integral formula, we can write the integration value as x power 3 by 3 with the limit 0 to 2 pi. And if you are applying the upper limit, 2 pi the whole cube minus 0 by 3. So we are getting 8 pi cube by 3, and if you are cancelling 1 pi, we are getting 8 pi square by 3 is the value of a naught. Next, an formula can be written as integral 0 to pi 2 pi 1 by pi 0 to 2 pi f of x cos n x dx. Here we have more than one variable lies inside the integrand part. More than one variable lies inside the integrand part. In this case, we can apply the Bernoulli formula, which states that integral u dv equal to u v1 minus u dash v2 plus u double dash v3 minus etc. So here we can take u as x square and v as sin nx. If you are applying the Bernoulli formula, we can choose always u as any one of the algebraic expression. We didn't use sine, cos, exponential as u, because if you are choosing like that, the problem will not come to the end position. Now u equal to x square, take the next derivative 2x, u double dash is 2 and then u triple dash is 0. Similarly, all the v's can be taken as a integrable values. v1 equal to integration of sin nx is minus cos nx by n. v2 is minus sin nx by n square, and v3 is minus of minus plus cos nx by n cube. So u v1, u dash v2, u double dash v3. On that way, we can apply the Bernoulli formula. So we can expand the Bernoulli formula. Then we are getting u into v1. u into v1 x square into sin x minus u dash into v2 plus u double dash into v3. After applying the Bernoulli formula, we didn't put the integral symbol. This is the integration answer. Now if you are applying the upper limit for all the three terms, here sine of 2n pi value is 0 if you are applying limit as 2 pi, and if you are applying 2 pi here, cos 2n pi value, and then here if you are applying sine 2n pi, this is also 0. So if you are applying the upper limit, the first and the last entry directly becomes 0 here. We are getting the value only for the middle term. Here minus of 2 into 2 pi into cos 2n pi value 1 minus into minus plus, so 4 pi by n square we are getting, and if you are applying lower limit here 0 square 0 as well as sin 0 0, here cos 0 is 1 but here we have x, so we are getting 0 and sin 0 0. So applying all the three applying the lower limit for all the three terms, we are getting 0 itself, and then finally we are getting 1 by pi 4 pi by n square. So pi will be cancelled, we are get an as 4 by n square. Next bn formula is 1 by pi integral 0 to 2 pi f of x sin nx in the interval 0 to 2 pi. Similarly, we can apply x square sin nx dx. Here also we can apply the Bernoulli expansion. U terms are same as the previous one. V equal to sin nx. Here V equal to sin nx and V1 is minus cos nx by n. V2 is minus sin nx by n square. In this way we can expand. So u into V1, u into V1 minus u dash into V2 plus u double dash into V3. So if you are applying the upper limit for x, upper limit as 2 pi here. So here 2 pi whole square cos 2n pi. Here also 2 pi we can apply. Sin 2n pi is 0 and then cos 2n pi. So the middle term directly 0 for both upper and lower limit. Sin 2n pi value is multiples of all pi's of sin are 0 as well as sin 0 is 0. So the middle term automatically moves. And only we are getting the values for the first and the last term. So minus x square cos n pi by n plus 2x sin nx by n square plus 2 cos nx by n cube. Upper limit is 4 pi square minus of 2 pi the whole square 4 pi square cos 2n pi value is 1 and then by n. Here 2 into 2 pi into sin 2n pi 0 and then cos 2n pi value 1, so you are getting 2 by n cube. If you are applying the lower limit 0, this becomes vanish. Here also this is 0. We are getting only for the last term 2 into cos 0 1, so 2 by n cube. Okay, now the existing terms are minus 4 pi square by n plus 2 by n cube and minus 2 by n cube. Three terms only we have remaining. Here also the two terms will be cancelled to each other. The bending one is minus 4 pi square by n. If you are cancelling 1 pi, you get minus 4 pi by n is the value of Vn. So we can substitute the value of A naught, An and Bn in f of x. Then f of x is equal to A naught by 2. What is the value of A naught? 8 pi square by 3 divided by 2. So if you are cancelling 4 by 3 pi square, the summation n equal to 1 to infinity, An value is 4 by n square cos nx plus Bn value is minus 4 pi by n sin nx. So 4 by 3 pi square, taking the constants outside the summation. So 4 into summation n equal to 1 to infinity cos nx by n square, taking minus 4 pi outside, summation n equal to 1 to infinity sin nx by n. That's all.